Okay? Last time we talked about standard normal distribution. That's a special normal distribution, as I said, a very special one. It's a normal distribution that has a mean 0 and standard deviation 1. Okay? So standard normal distribution is one of the normal distributions that has a mean 0, standard deviation 1. And to do that, to do any problem related to standard normal distribution, we use this standard normal table, right? We've been practicing that, so I hope you know how to do that. Okay? This table, standard normal table. And this is the last example we mentioned last time. If we wish to figure out the percentage distributed between negative 1.4 to 2.33, what we need to do is use that standard normal table. Help us to find the area under this standard normal distribution curve. Okay? That area actually is the percentage. And the standard normal table actually gives us those area under the curve. From 0 to some point away from 0. Okay? So we have a point 2.33 to the right of 0. Then the area from 0 to 2.33. That information is given in the table. What you need to do is use this information, 2.33, to help you to look up a standard normal table and find the area from here to here. What about the area from 0 to negative 1.4? We say that the curve is symmetrical, right? Symmetric with respect to 0. So the area from 0 to 1.40 is the same as area from 0 to negative 1.40. So in order to find the area from 0 to negative 1.40, well, just find the area from 0 to 1.4. That's it. Okay? Don't be scared by this negative and not seeing any negative score here. Well, you don't need that because of the property of symmetry. This table is good enough. This table only covers area above 0, but that's good enough. Below 0, you still get area. But remember, those are area. So when you check the table, you find this is the area. Right? This part is the area. The information give you on the table is an area. Okay? You know the area from here to here. You know the area from here to here. You simply just add them up. You can get the area from here to here. Okay? And so that's why I say when you do these problems, draw a picture. You will be able to understand whether you should subtract or add. Most of the time, students have trouble determining whether you should subtract or add. Right? This curve describes a distribution. Okay? That area is like percentage. You know the percentage from 0 to here. That's a positive number. You know the percentage distributed from here to here. That's a positive number. So the percentage from negative 1.4 to 2.33 should be this percentage plus this percentage. So you add them. Okay? So that's how you determine whether you should add or subtract. It's not because you have a z-score that's negative. That has nothing to do, with because of that sign. It is because that you have this piece of area here, you have this piece of area, and then these pieces of area, they're all positive, or these percentages are all positive, so you add them. Okay? I think I mentioned to you an example too that when do you do negative? When you have the same situation, similar situation, and let me flip to Elmo. You have a similar situation. This is a bell-shaped standard normal curve. You have 0 here. Instead of having negative 1.4, you have a positive 1.4 here, and you have a 2.33. And if you wish to find the percentage or area in this part here, you got to find the area or percentage for this part, and then find the area or percentage for this part. This one subtract this one, you get this area. Okay? Area from here to here, subtract the area from here to here, you get this area from here to here. That makes sense, right? Yeah.
Basically, they're both positive numbers you subtract. If one's positive, one's negative, you add.
That's a good way to look at this, right? It's kind of giving yourself a rule. If both are negative, you will subtract too. If both are positive, you should subtract. That's a good idea, okay? But it'd be good that you can draw a picture and visualize the situation, right? That make it more clear to you. Okay, that's a good idea. Okay, so for this one, we check the standard normal table, find out area from 0 to 2.33 is 49% or 4.901. Area from 0 to negative 1.40 is this. We simply just add them together. We get 0.9093. So the percentage distributed between negative 1.4 to 2.33 is about 90%. If this is a distribution of like bone density scores, okay, and this tells us, well, those people whose bones, what percentage of people whose bone density is between negative 1.4 to 2.33? Oh, bone density score, right? This tells you that it's about 90 about 90%, 91%. Okay, if we can use the standard normal distribution to describe the distribution pattern of all the bone density score for the maybe just the female, let's say, okay, population. Okay, so if that's the case, I can estimate actually the distribution of bone density in any range. If I ask you what percentage of the women with bone density between 0 to 2, well, you just find use the Z table, find out area from 0 to 2, and that's percentage, right? That's about 47% if you check the standard normal table. Okay, so this is a really interesting and very powerful thing. Okay, but this here is just for standard normal distribution. Now, in real life, most of the distribution are not standard normal, right? You look at the pulse rate. We may want to use a normal curve to describe pulse rate distribution. Now, pulse rate doesn't have a zero mean, doesn't have a standard deviation 1, okay? So how can we deal with those kind of problems? Well, it's simple, actually. We can still use the standard normal table to help us solve the problem, okay? And then when we go, the way we do it is, because this is an important theorem, right? This is a theory that developed or derived by a mathematician, okay? So now, theory is sometimes too abstract for people to understand, but there's really a lot of good use for them, right? People derive mathematical theory, and then you can use it in application, make use of good mathematics that have been derived, right? Mathematical theory that has been derived, okay? And this is an important theory, right? We don't like those abstract theory, but we'd like to apply those theory, right? We don't we're probably not capable of actually derive or understand how it is derived, but we'd like to know how we can apply it. Here, the theorem is, if you have a regular normal distribution, a bell-shaped distribution, that has a mean mu, right, the mean of a distribution, and you have a standard deviation sigma, okay, I can standardize this whole distribution. How do I standardize that? Remember we learned a z-score earlier, okay? We just use a z-score formula to standardize every single point in this distribution. Right, so remember, this is that formula. You have a value, subtract the mean of a distribution, divide by standard deviation of the distribution. You do that for every single value in this distribution. The resulting score follow a standard normal distribution. Right? If the original distribution is regular normal distribution, and then if you standardize every single point in this original distribution, the resulting distribution will be standard normal distribution. Okay, how good is that? Well, actually, very good. Let's say this is the original normal distribution. And I'm interested in finding the area or percentage lie between 2 point A and B. Okay? Now, if I can standardize this distribution so I get a standard normal distribution, okay, the percentage lies between standardized score of A and B. Right? So you standardize A and standardize B. Okay? So that A becomes this point when you standardize A using the standardization formula. And standardize B will be what? B minus mu divided by sigma, right? Using that standardization formula as finding standard score. The percentage lie between these 2 points in the original distribution, right, is the same as the percentage lie between these 2 standardized points under the standard normal distribution. And I can use a standard normal table to help me to find the area for this piece, right? And that area is exactly the same as this one. Okay? So that's a theorem that we can use to help us to solve normal distribution problems for any kind of normal distribution with just one standard normal distribution table. Hope that makes sense. I have an original normal distribution. I wish to find the area between A and B, or percentage lie between A and B. What I do is just standardize this A and B. Okay? So how to standardize A? Using the standardization formula. I use A subtract mean divided by standard deviation. How to standardize B? Use a B minus means divided by standard deviation. All right, so the area under the original distribution between A and B is exactly the same as the area under the standard normal distribution between standardized A and B. So to solve this problem, originally I have this event. So what I do, I just standardize these 2 points. I get these 2 numbers, right? And I use a standard normal table to find out what's the area under the standard normal distribution between these 2. And that will be the answer to this. Okay? It's easy to say it. Let's try some example. Right? Here we have a normal distribution. this normal distribution has mean score 5, standard deviation 10. And I want to find out what percent of this distribution that's between 5 and 6.2. Okay, so this is that normal distribution that has a mean 5 and standard deviation 10. And when I solve this problem, I always draw this picture to help me to understand what's going on. I will mark the location for mean, that is 5, and also write down the standard deviation somewhere to help me to understand that this distribution has a standard deviation 10. And I wish to find the percentage distributed between 5 to 6.2. How do I do that? According to the theory I just mentioned, if I'm able to standardize this endpoint, okay, I standardize 5. Whenever you standardize mean, you're going to get 0 because when you do standardization, you use that number, subtract mean, right? Mean is 5. You use 5, subtract 5, you get 0. Divide by standard deviation, you get 0. So mean always standardized to 0, okay? And your 6.2, if you use a standardization formula, 6.2 minus 5 divided by 10, you get 0.12. So the standard score for 6.2 is 0.12. Okay? This is standardized A, this is standardized B. Okay? Or this is standardized value for 5, this is standardized value for 6.2. My theorem says that the area under the standard normal curve in between these 2 points will be the same as area under this original normal curve between these 2 points. Right? Or we say the percentage lies between these 2 points, standardized points, right? Will be the same as percentage lies between these 2 points. So what I need to do is just find the area from 0 to 0.12, right? If you check the standard normal table, that area is actually, whoa, what happened? Oh, here, okay. If you check the standard normal table, that area is 0.0478. This is 0.12, right? So for this column, look for 0.1 and then look for second decimal 2, right? 0.0478. That's a percentage or area for this region here, under the standard normal curve. But that's actually the answer to the problem, right? The percentage lie between 5 to 6.2 is the same as the percentage lie between 0 and 0.12 under the standard normal curve or normal distribution. So you can answer the question, right? In that original distribution, the percentage lies between 5 and 6.2 is this 0.0478 or about 4.78%. Am I making sense? Let me go back again, all right? The situation is here. This is what we're looking for. We'd like to find out the percentage lie between 5 to 6.2 in this distribution. That's a mean 5 and standard deviation 10. To solve that problem, the first thing I would do is standardize these 2 endpoints. So 5 be standardized to 0. 6.2 be standardized to 0.12. Right? What formula do I use? I use the standard score formula. Okay? So I standardized 5 and 6.2. I got these 2 points. And the area under the standard normal distribution lie between these 2 points will be the same, exactly same as this area. Okay? So what remaining is just find out what this area is, and that's the answer. Okay? Use a standard normal table. And standard normal table tell me that this area is actually 0.0478. So that area in between 5 and 6.2 is 0.0478. So if you're interested in what percentage of a distribution lies between 5 and 6.2, that's about 4.78%. And that's the answer. Okay? So, but solving this problem, the student have to rely on that standard normal table. Okay? You don't need another table to solve this other normal distribution. If that's the case, it would be terrible. Every time you look at a variable, it has a different mean and different standard deviation, and you have to produce a table for that. That's the infinite many table you have to produce, right? With this theorem, you don't need to. One standard normal distribution table takes care of any kind of normal distribution problem. Okay. Let's look at this one. The same setting. Mean is 5, standard deviation is 10. I wish to find the percentage lie between 3.8 and 5. Okay. So I have a distribution. Again, this normal has a mean 5 and standard deviation 10. This question now is interesting in percentage lie between these 2 points. So what do I do? First, I will draw a picture. I'm interested in finding the area or percentage between 3.8 to 5. So what I do is standardize these 2 points. Mean is still, again, standardized to 0, right? Because you're going to have 5 minus 5 divided by 10. That's 0. And then 3.8 will be standardized to negative 0.12. Okay, if you use 3.8 minus 5, minus mean divided by standard deviation, you get negative 0.12. And what's the area here? Well, earlier example, we found the area from 0 to positive 0.12. It's the same as area from negative 0.12 to 0, right? So exactly the same number, 0.0487. So percentage lie between these 2 points is about 4.78%. Okay? And you need that standard normal table. Okay.
How would you use this in a practical? You said something about blood pressure didn't have it.
Well, yeah.
How would you, I'm trying to...
For instance, the blood pressure, right? Maybe high or low, whatever, okay? Maybe let's say we have a particular type of patient, blood pressure has a mean of maybe a high as let's say 110, okay? With the standard deviation 10, okay? And is 110 normal? Probably, right? If we consider 110 as normal. And then if you have that normal distribution bell shape that has standard deviation, did I say 10?
Yeah.
Okay. Now, if you wish to find out what percentage of these people whose high blood pressure is above 120, okay, you can estimate that with this normal curve. If you want to get a sense, right? If people told you that the average blood pressure is 110 with standard deviation 10, then people ask you, oh, what percentage of this population has blood pressure above 120? Well, you should know it. When you know the mean and know the standard deviation, also know that it's a normal distribution. You actually know everything about this distribution. People ask you what percentage of blood pressure is less than 90. You'll be able to calculate it using the standard normal table. If people summarize that using a normal curve and with a mean and standard deviation.
So with the result, the number of people that are above 120 would be your Z table?
Well, you can use this problem to solve it.
What does the Z table?
This example, type of example.
The Z table tells you what's under that. The
Z
area
table
under
is this, yeah, area under the curve between 0 to a Z score. Okay, let me deviate a little bit. Just maybe answer that question, how do we do that, okay, since we're talking about it. So, I have a paper here. So, let's really assume that we have a mean of, let's say, 110 and standard deviation 10 for blood pressure, okay? And you're interested in finding the percentage of this population whose blood pressure, let's make it, how much you want to say? 130? Okay? So if people describe to you the distribution of blood pressure that's bell-shaped, with a mean 110, standard deviation 10, what percentage of this population have blood pressure higher than 130? You can solve it now. Right? To solve it, well, I always like to draw a picture. And I'll mark the mean. Mean is 110. Okay? And we're interested in percentages higher than 130. So I'm going to mark 130. I know that it's on the right. And so I'm interested in this, actually. The proportion that is higher than 130. Okay? And how do I solve this problem? I don't have a table for this problem directly, for the mean 110 and standard deviation 10, but I do have a standard normal table. Okay? So I'm going to use that theorem that I just mentioned to you. Now, to do that, I would first standardize it. This is our original score. I want to standardize it. How do you standardize? The standard score for this is 130 minus mean divided by standard deviation, which is a number, very nice looking number, 2. So the Z-score for this is 2. Okay? Now what we're looking for is what? We can do is what? Using the standard normal table to find out what proportion of a distribution that is to the right of this. Right? In this case, you can cover this up, assuming that this is a standard normal curve. Okay? And then the 2 is this point here. And 0 is this point here. Okay? And how do you find the area above Z equal to 2? This is the same as finding the area above 2. Okay, what would that be then? You look up a standard normal table for Z equal to 2. Z equal to 2, what is that? 0.4772. Okay? 0.4772 is really this part here. Right? Table give you the area from 0 to some point away from 0. Right? And here we're looking at 2. So for 2, that area is 0.4772. But this is what we're interested in. Okay? So we got to use 1 minus, if we know the area below, I'm sorry, I should say, area between 0 and 2, which we can find it from the table, 0.4772. So this is really just 1 minus 0.4772, which is what, 0.0228. So less than 3% of the people whose blood pressure will be higher than 130.
Okay, so you convert to 0.0228 to a percentage.
Yes,
That's
you can.
the unit.
If you're asking percentage, right,
Okay.
then that's the percentage. Yes.
Wouldn't it be 0.5 minus 0.4772, not 1?
Ah, did I say? Oh, yeah. I was saying, I meant 0.5. Okay.
Still comes out the same.
Well, I was thinking 0.5, but I put down 1. That's why it come out the same. Okay. It should be 0.5. Great. Thanks. Okay. Good. Good. You really know it, right? Okay. So you see the use of this. Why we need this. Okay. Now, and it's so handy. Now, if we know the mean and standard deviation, you can report this population, distribution of this population by just those two simple numbers. If you know these two numbers, you can take care of any, but again, this is normal distribution only, all right? If the distribution is bell-shaped normal, then you can use this always to approximate what percent of the distribution lies in whatever range.
Dr. Chang,
Yes.
what was the 0.5 part? I missed that for some reason.
Okay. We have here to here is 0.4772, right? But everything above this is 0.5, half of the area, right? So use 0.5, subtract this piece, I can get the tail. Okay. Excellent. Excellent. Okay, you can do this, then I guess I don't have to go through all these other examples. But I should go over it. Right? Okay. So let's look at like another example. The same distribution, mean 5, standard deviation 10. How can I find the distribution lies between these two values, 2.9 and 7.1? Well, again, what I would do is draw a normal curve first and help me to understand what kind of situation I'm dealing with. Right? Mean is 5, so this is a range covered from left of mean to the right of mean. And then what I do next is standardize these 2 points. 2.9, standardize it, you get negative 2.1. 7.1, you standardize it, you get positive 2.1. So what you do is check the standard normal table to find out what's the area from 0 to 2.1. Twice of that will be what? That will be the area from negative 2.1 to positive 2.1, right? So actually, each piece is about 0.0832, so the total is 0.1664. So the total percentage lies in these 2 points, about 16.64%. And this is approximation. In practice, this would be approximation, okay? You can never really have an exactly normal distributed population. This normal distribution is a mathematical model that people come up with to help us to, simplify help us to actually solve problem easier, to help us to be able to approximate the percentage, right, distributed in any range, right? It is not exact, in the actual population, it's not going to be exactly 16.64%, but you get an idea, right? It's roughly 17% of the distribution will be in that range. Okay, it's an approximation, okay, if you really use that in application.
I have a question. I forgot my book now.
Okay.
What number did you look under the Z table in this example?
This is 0.21, right?
Okay.
0 to 0.21.
Okay.
Standard normal table allow you to find the area under the curve from 0 to some point away from 0.
Okay.
Okay, so you look for 0.21. You will get that number, right? 0.21, let me quickly flip to 0.21. Zoom it in. 0.21, that's 0.0832. Okay, that's how you get it. All right? Good. So how about the next one? Greater than 8. This would be the example, similar to the example I just shown you. We have this normal distribution, mean is 5, standard deviation 10. I wish to find a percentage above 8. So what I do is standardize this value 8, right? Subtract mean, divide by standard deviation, I get 0.3. Okay? And how do you find the area above 0.3? You find the area from here, too, first. And then subtract from that number, from 0.5, you get this tail area 0.3821. Okay? If you look up the standard normal table, 0.3, what would that be? 0.3 give you 0.1179. Subtract this from 0.5. You get the 0.3821. Okay? Makes sense? You look up the table. This number actually gives you the area from 0 to 0.3. But in this example, we're interested in finding the area above 0.3. So how do we get that then? We use 0.5. Subtract, right? Area above 0. From here and on, that's 0.5. Subtract this part is 0.1179. You get the 0.3821 on the end. Okay? Make sense? Okay. Let's look at more example. Maybe some statistician, right, collect these data and realize the number of hours worked per week for residents in Ohio has a normal distribution. And they report you that the mean is 42 and standard deviation 9. Right? So we are hardworking people, right? More than 40 hours. But if people ask you this question, what percentage of Ohio residents whose work hours are between 42 to 60 hours? Can you approximate that using normal curve? Yes, we can do that now. What about what percentage of people work less than 20 hours per week? We can do that too. Okay? Any range you specified, we can do that using that standard normal table. So let's look at this 42 to 60. We know the mean is 42, right? So if we standardize 42, we get 0 always. 42 minus 42 is 0, divided by 9 is 0. Then we standardize 60. 60 minus 42 divided by 2, we get 2. And then we use the standard normal table, find the area from 0 to 2. Right? And that's 0.4772. So that means the percentage of people who work between 42 to 60 hours, about like 48% of them. Okay, again, use a standard normal table. So that's the answer. Are we doing okay? Is everything following?
And the problem before that,
Mhm.
and you want to put negative 0.3821, and the one we just did before this.
Earlier, negative. This question, right? We know the area from here to here is 0.1179,
Right.
and we wish to find the area above this point.
So you subtract it from
You subtract 0.1179 from 0.5 because we know the total area above 0 is 0.5. Okay, if we know this piece here, we subtract that from 0.5, we'll get this tail. Okay, consider those are area, right? Okay, it won't get negative. 0.5 subtract 0.1179. Right. Larger subtract smaller, right? 0.5 is the larger piece and subtract the smaller. Okay, good. Okay, so this one we know what happened. Okay, now how about this one then? Less than 20. How do we take care of the less than 20? Distribution is like this. Mean is 42. This thing is not working quite right. Okay, mean is 42. 20 is here. We're interested in percentage below 20. Okay, so what we do, standardize this point. If you standardize this point, subtract 42, divide by 9, you get negative 2.44. So that's here. To get this area, what we do, we find the area from 0 to negative 2.44. Okay, and what we do then? Subtract that from 0.5. Okay, or we say 0.5, subtract this area, then we get this tail area. And the area from 0 to negative 2.44 is the same as area from 0 to 2.44, right? So you just use a 2.44, check the standard normal table, you'll be able to get that. And so the tail area actually is 0.0073 because if you look at the table, 2.44, I have to zoom in back up, 2.4, and 4 will be this one, right? This is 4. Okay, 2.44 is 0.4927. 0.4927 subtracted from 0.5 again. Right? Subtract this piece from 0.5, you get 0.0073. Okay? So that's pretty simple, right? This is a piece of cake. Right? But you have to practice. A lot of time, even my son said, it's easy seeing me showing them how to do a problem, but when you really try to do a problem, it's a different thing. Right? So you need to practice and gain your experience, and you'll be able to do well, okay, on these type of problems. So how about let's try some problems, okay? How about let's try to use this parameter. Maybe the test score for the first exam, well, no, that's too few, small population. Okay. How about the brain weight for nurses? Okay. That has a mean of 2.2 pounds and standard deviation of 0.3 pounds. Well, is that, no? This is just pretending, right? The brain weight for a particular type of people is 2.2 pounds as a mean and standard deviation 0.3. What percentage of this population that has brain weight higher than 2.6? Can you do that? That's number one. Number two, what percentage of people whose brain weight was between 2.4 to 2.6? Okay, can you do this? You're going to share the table with your neighbor, okay, so that you solve the problem. Okay. We are assuming that this is a normal distribution. Normal distribution mean 2.2 and standard deviation 0.3. This is pound, okay? So I wonder if I put this on here, you can see it or not. It's just, let's try it. Can you kind of see it? It's hard. It's too blurry, huh? Oops.
Thank you.
Anybody finished? You finished?
Yeah, I am.
Uh,
I got sloppy
okay, this one is about everything above 2.6, so it should have a tail area.
all the way up to
Right.
there.
That's above 2.6. Yeah.
So I want this
Yeah.
area.
Yeah. Mhm. You done? Is that oh, here. Okay. Oh, it's 1.3. Okay. So okay. Okay. You're trying to say that this is between 0 and 1.3, I guess. This one. This is a bit confusing. Think about it. This is from 0 to 1.3, right? Here to here, right? And then, so that's this. And use that subtractor. Okay, yeah, that's You got it? No? Yeah? How about you? Okay. So that's, you're going to need to find a difference, right?
Yes.
Yeah. Mm-hmm. Oh, okay. 21. Okay, good.
Is that it then?
Yeah, that's good. And you have 0.67 and 1.33. So the difference, that's good. That's good. Mhm. Okay, let's quickly get this done. All right. You can help me though, right? This is actually really just the area above the standardized score of this. So you use 2.26 divided by 0.3. So that's area above. Someone say this is what? 1.33, right? When you're doing this problem, try to keep 2 decimal places so that you can use this table, because the table covers up to 2nd decimal place, right? So when you calculate z-score, keep it up to 2nd decimal place. So you're looking for area above 1.33. Now 1.33 is 0.4082. 0.4082 and 0.5 subtract that, right? Oops, I'm sorry. Let me write it again. It's 0.5 subtract 0.4082. Okay? Why? Graph is like this. This is 2.2. Somewhere is 2.6. The z-score for this is 1.33. Z-score for this is 0. Okay? We're looking for this area here. This is z-score. This is original score. So if you cover this up, find the area above 1.33. How do you do that? You first find the area from here to here. That's 0.4082. So this tail area will be 0.5 subtract this piece. Right? So that will be what? 0.0918. That's it. That's the answer to this. Okay? For this one, use another pen. Mean is 2.2. You're looking for 2.4 and 2.6. Interesting in this area, right? This is the original score. Let's find a z-score. Z-score for 2.2 and 2.3 is 1.33. We got them already, right? 2.6 minus that. So in fact, this is really just area from 2.4 minus 2.2 over 0.3 to 2.6 minus 2.2 over 0.3. I'm just standardizing these two values, okay? So that's actually is area from, what is this? 0.2 divided by, that's 0.67, right? So this is 0.67. So you look for 0.67. This area will be area below this 0.4082 minus area below this to 0, right? 0.67. Okay, 0.67. I'm sorry, let me find this 0.67 first, right? And I'll, for 0.67 is 0.2486. So this 0.2486. Area from here to here is 0.2486. Area from here to here is 0.4082. So 0.4082 minus 0.2486. That's the answer. So what would that be then? That's going to be 0.1 5